This is using feedback so that you can basically do computations on the GPU, except that instead of using OpenCL or CUDA or compute shaders or some other fragment or framework that's actually designed for it, we'll just use our current Vertex shader programs and do computation using them. I think it's a good introduction to the computation part since it follows right into what we're doing. But it's also kind of a way to do computation on the video card for 3D graphics in particular, kind of graphics-focused computation. And this tutorial does nothing of the sort. It actually calculates the square roots of an array of 5 numbers, and it doesn't even draw anything. I'm just going to show you what it does. I should probably put this line on top of the tutorial at the bottom or somewhere, because it might take a while to work out. Graphics.
Some notes are on software.
This demo is.
Oh yeah, which is the source code.
Yeah, it's in the. I don't have SFML on that. So first step to compiling it is install SFML. You see I put all these flags in here for SFML. Search SFML. It uses a library called SFML that we haven't really talked about a lot. And so there's a libsfml, and we can install a dev package for it. Okay. I'm glad the network works. I really kind of needed the network for this class, and I knew I needed the network for this class. So I was slightly concerned when the network was broken. I was very relieved when I could first ping the outside world. I was like, hey, I know I can fix this now. Okay. My apologies that nobody else has worked. I see you're sitting at a computer that's sadly useless. Okay, try building this thing again. There's like a whole bunch of problems, actually, for some reason, even though this thing compiled fine before. And so now I'm not sure why. Because those are like, it's trying to compile the Vertex shader source code. Is that supposed to be an R? Would that be the problem? Well, I'm not really sure. So for some reason, you can see the problem here is it's trying to build the source code there. So it's seeing this pound version and saying, wait a minute, that's not part of C. And it's right, it's not. So I'm wondering if that letter right there has changed. I almost never use multi-line strings. And so I'll go grab the version I was working on at home. I think it's kind of 8. That's supposed to be an R, all right. Oh, maybe I didn't say G++. That might be it. Okay. Everybody's watching me trying to figure out how to compile something. So far, our class is really, really entertaining.
Use GCC.
Yeah, but it doesn't work.
What's it doing?
It's not like in my multi-line string. Oh, what if it's using a different standard? There we go. That's it. Okay. So the reason that didn't work, since these ones still run on Ubuntu 16.04, 16.04 has an older version of GCC than the one that I was using to build these on Debian earlier today. The newer version I was using on Debian earlier today is defaulting to a newer C standard that respects the R quotation mark convention for multi-line strings that I have very little experience with since it's just been added to a recent C standard, C++ standard. All right, okay. So now we know the problem there. So let me go ahead and put this into the file. If we say echo that, and we just print it out. If we put it like this into that file c8.cpp, and take the c8.cpp and take that thing there and put it right up here, and then we put a / before it and say compile with that, and then we SCP that back to our software where it came from, and then we will spend a lot of time on this. Okay, so what does it do that is useful? It prints out an X bad problem. Oh, that's great. This is really useful. I'm surprised that it does that because, like I said, it worked just fine at home before I brought it here. So let's do this then.
It's one of those issues.
Okay, we'll copy it to Nimrod. And it will SSH in Nimrod. And then we'll take the top of the file where we just conveniently put the way to compile it. And then we'll try and compile it on Nimrod, like that. And then we'll run it. And it'll tell me it can't open the display because, of course, we're logged in remotely. But then we'll say display equals :0. We'll say export that, actually. And then we'll try and run it. And then
It still doesn't work.
it will hang forever. Oh, this is great.
Doesn't that mean it works successfully?
If it hangs forever?
Is it
Just
just
how this program.
Is it, oh, so this one's supposed to have something like that?
This is supposed to print out some stuff. Okay. Okay. Oh, I know. I thought I was my wife earlier. Okay, so apparently, even the version I compiled before now hangs forever, despite the fact that it worked great an hour ago. All these kind of demos. And the fact is, I was even working remotely on the system with display exported as :0 before. So it's doing like the exact same thing. I guess I connected from a different machine. But other than that, it's all the same. So my demo is very broken today.
Wait, does that have an IP?
Do I have an IP? Yeah, oh, I fixed mine.
Oh,
I just made myself an IP. I'm number 30.
okay.
Okay, well, anyway, so I'm not sure why my demo is completely broken today. I'm surprised about that. What happens if I try and recompile it? Oh, maybe it's I've been building it with std equals C++14. We'll try one more attempt here. And then if that doesn't work, I'll just explain what it used to do. And that'll be really boring. Okay. I spelled that wrong. It's not Steam as much as Valve would like it to be. Window graphics. Undefined reference to main. Oh, I didn't bother to say what file we're compiling. You know that's important? I guess. Okay. So, a little stumped as to what's going on here. Let's take a look through the program. And this one's all stuffed full of extra stuff that doesn't belong there. That'll be okay. Okay. So what the program is supposed to do, and what it usually does, is calculate the square roots of 5 different numbers that are stored up there in that GeoFloat data array. And notice it's not printing out anything at all. So as I explain this, we'll also see how far we're getting at the same time. So it seems to know about printf, although there's no stdio here. Go ahead and include it. So I'll say printf made it. Okay. So first thing, we got this. So this bit up here uses SFML to do the same thing we've been using glut to do for a long time. I thought about trying to just taking a tutorial and changing it to work in glut. And maybe if it continues to insist upon not working, we might do that real quick, but I don't think we will. Anyway, so this part sets up a window using SFML, same thing we did in glut. You can probably look through it and see where pieces are that make sense. Video mode 800, 600. You know, 10 guesses what that does. Where's that go? Probably the title of the window. So you can kind of figure out what's going on there, but it's just using a different library than glut. SFML is more complete. It's got libraries for sound and multimedia and that kind of thing. But since it's a larger, more complete library, it's not really it does a lot of stuff we don't need it to do for graphics programming, so we haven't used it much. Anyway, but it's a glut competitor because it solves a different problem. It gives you kind of a unified game development library with many useful features, as opposed to just a graphics focused one. So, you know, it's like you needed an engine and you got a car. Okay. Anyway, so we load up SF here, and load up our window, and so making it that far. You know, weirdly enough, we're not. We're making it that far. Very first line, right there. Yeah, we are. We're just hanging on creating a window stuff. Makes you wonder if I get the export botched somehow. That's normally what I type. Botch it. Okay. So anyway, continuing down. The next thing we do is initialize glue. The GL, so more libraries. We've been using glue occasionally for stuff. I think this is actually the only lines that talk about glue. And obviously we're not making it there, since I think probably where we're hanging on is right here at that SF window. And so that's why I think that perhaps we just take the whole thing and transplant it into glut. It'll start working without us ever figuring out why it didn't over here. And then that'll be a funny mystery for me. I'll probably go home and it'll work right, and then there won't be any way to try to debug it at all. And so probably this has to do with me standing here instead of standing somewhere else. You know, we're logged into a computer that's like, you know, this is my computer at home. Okay. So then the shader. We've been doing compiling shaders for a good while, and this one's really no different than any other. We have this is tagged at version 150, and we got this in-out thing up here. Now here's what's different. This shader doesn't ever say what GL position is. Normally the vertex shader determines what position your vertex is supposed to be at, and that's its main purpose. So this one, instead of that, we've got an in value, we've got an out value. We're just going to say the out value is the square root of the in value. That's it. So about the simplest shader you could possibly contrive here. It's just it does something a little different. Okay. So then after that, we compile that and install it kind of like we had before. We make a program and attach a shader. Now all we did is make a vertex shader. And early on I said you need a vertex shader and you need a fragment shader. There's no fragment shader in this program. And that's not why it's hanging up, by the way. So the lack of a fragment shader is not a problem because we're not actually going to draw any fragments. When we get close to the right point, we'll actually turn off the rasterizer and not make any fragments. And so the fragment shader is never needed. Anyway, we go ahead and add that one on there. So now this out value, you got to set up the out value. So instead of setting GL position here, we're actually coming up with this out value related to the in value. And so we set up a feedback varyings to hold that. So the feedback varyings here, this is actually kind of an older way to set these things. Since OpenGL 4 something, that's not actually the way these things have been done. Typically everything's been set up with a well, everything can at least be set up on a shader. But what we're setting up here is a transform feedback buffer. And so these are our transform feedback varyings. Remember, it used to be a varying attribute. When you set it in the vertex shader and read it in the fragment shader, that was the initial term. Newer OpenGL uses in, out. But the word varyings is still here in this function call. So that's what we're doing. We're setting up something to be a variable in the sense that it's an out from the vertex shader. And then we just have one array for it. We got one feedback varying that we're going to have, this one right here, out value. And it's going to be an array because, of course, we're going to run this program a bunch of times at the same time. And so that's where we get to the whole varying thing. Okay, that's built, and we'll have varyings from that. So then we go ahead and link the program and use the program, kind of same things as we did before. Oh yeah, one important note about this line. This has to be set up before you link the program. Otherwise, it won't know where that's going. It'll say, there is no matching out in the fragment shader. So we don't want it to say that. We want it to know that that's what the out value is for. It's supposed to be received here in a program. It's not supposed to be received in a fragment shader. We didn't explicitly say that we don't have a fragment shader, but of course we don't. And so that's where that's going to go. Okay. So once we got it all linked and used, then now we're ready to create a vertex attribute array and some vertex buffers to go with it. Now, here's an important point about doing this transform feedback. For a good while, I looked at this thinking that, well, surely you can change a buffer, right? Take a buffer as input, use the same one for output. But you can't say in-out for parameter on one of these vertex shader programs because a basic limitation of OpenGL here is that you can't have output go to the same spot as the input for any shader. The shader's got to put the output somewhere else. And I'll explain that a little more when we get to geometry shaders and how to use them with this stuff. Okay, so that's what happens with the shader thing right there. Okay, so once we got the vertex arrays, so we're going to set up two buffers here, one for input, one for output. So this is going to be the data for the initial run on here. We just got 5 floats, and we can get the, hey, you got it. What was wrong?
The DHCP server was unplugged.
Unplugged?
Unplugged. Somebody had unplugged the DHCP server.
Probably trying to fix things.
Probably, yeah.
Or maybe they unplugged it a long time ago and the computers have been
That's
just
possible.
using their old leases.
So I plugged it back in, marked its line with tape, and taped it into the power strip. So it shouldn't get overwhelmed.
Cool beans, thanks.
And we heard back. You just have to.
You got to run the internet. You got to release and renew on every computer now.
Okay, yeah.
Or run the fixed internet.
Cool. I think I'll leave this one alone since it's since I already set it up. But it'll get rebooted like in an hour anyway.
Did you set your IP up so it's static?
If you statically set it, it's probably going to stay as that.
I disabled the network management manager service because I didn't want anything to do with it. Then I set a static IP temporarily for the moment, and then I set a route manually, and then I set the DNS server to 8.8.8.8, and then everything worked. However, when I reboot it, Network Manager will come back on because I didn't disable it permanently. I just turned it off for the moment. And Network Manager will hopefully manage to do the right thing.
Sweet.
Yeah.
Now trying to do extensive testing of the network information. Really.
Oh, so to bring you here, since you're, if you fix the network problem, your brain's probably in overdrive. So just look at that, and then you'll know what we're doing.
Oh, yeah, that makes sense.
Okay, cool.
It's okay, Jesse. We got a video of it.
Okay, so for a long time I was trying to make in value and out value the same thing, so I felt like you should surely be able to do that. You can't do that. So now I'm confidently proclaiming that and saying you can't make them the same. So somebody is probably going to punch this into Google and find out that 2 hours ago it just got added to the OpenGL 4.6 standard. And if so, just tell me. I'm glad to know.
Jesse's going to find out.
So why are we trying to get the square root?
Because we want to know it, and it's really slow to calculate 5 square roots on our 6-core processor, so we're going to use the video card instead. Okay, so we got to set up 2 buffers. One of them to put these speed values in, one to take them back out. Okay, so the first one here, this is going to be the VBO, which is the vertex buffer array. That's where the vertices all start. The other one's going to be the TFO, the transform feedback buffer. These names are not special. These names were made up by the tutorial authors because they made sense to the tutorial authors. So there you go. Okay, once we've got so we have to set these 2 things up. So we call GL gen buffers to generate the buffers, and that doesn't actually allocate the space on the card. The GL gen buffers. I went through this 3 weeks ago. I probably everybody's forgotten, including myself. So I'll go through it again. This makes a buffer. It says that, well, we're going to have a buffer, and OpenGL should make a buffer for us, but we don't know how big it is yet, so it's not going to allocate any video memory. So I'm going to bind buffer, and binding a buffer makes it current. So whatever you're currently reading from is the thing that's currently bound. Remember, OpenGL is a state machine. And I realize that state machines are not the way libraries are usually set up. I mean, if if you think about a favorite library of some sort, think about the math part of the C standard library. You don't set an input as a state and then run the sign function with no parameter and expect it to give you the sign of the currently bound number. It's just not how it works, right?
No.
Yeah.
So why don't they object oriented?
So the reason it is a state machine, a lot of hardware is a state machine. In fact, most hardware is a state machine. So for example, when I was writing device drivers for this audio sampling thing, you would set the card going, and that was a state. You could set each of its registers to some value, and that was how you set it up. So if you wanted to do something, you put the right values into the right registers, and then you told it to start. And whatever state was in, that's where it started from. And so that's very typical in the hardware world. If you think about your garage door, it's just, okay. I'm presuming you have an automatic electrically operated garage door, and I may be very wrong about this. I haven't had one for all of my life. It's been extensive times I've lived places that didn't have it. But if you think about one of those automated garage door opener gadgets, it has a state. It's open, it's closed, it's stuck halfway in between, it's just been reset, it's going back up because the cat tripped the beam while you were closing it. It's got some state, right? And it's got a lot of possible states, but it's definitely in some kind of state. So what happens when you push the button? Depends what state it's in, right?
Cross directions.
Yeah, well, or stops if it's in a moving state. Yeah. Or if it's in a command state, it may do something completely different if you've been holding down buttons on it to configure limits or something like that. But it's always done in a state machine. So that's how hardware works. So state machines are kind of inconvenient to use, even though hardware is a state machine. I mean, the buttons on this thing have a different effect depending on how that thing is, what state it's in. But usually if we're writing a library, we avoid state machines because you have to remember what state it's in all the time. And also it has a state, so if it has a state and you want to do something else that doesn't depend upon that state, then you need to take it out of that state and put it in the other state and do whatever you're doing with it and then put it back in the state you actually want it. You see how it's a hassle. So that's why most libraries don't use state machines. However, OpenGL tries not to completely hide the nature of what you're controlling because you want to be able to control it in an efficient manner. And so if we hide what it is, make the equivalent of Python, then you can't run it in an efficient manner anymore. Now somebody could make a library over top of OpenGL that does away with the whole state machine thing and does it in an object-oriented way. And each object has some sort of state associated with it. And when you do something on one object, it just transforms the state to match what it needs to be to do whatever command happened. Yeah, you can totally do it. But it would hide a lot of the details of it. I'm sure there's some library over OpenGL that does that. Anyway. And this is actually the trend in graphics APIs has been away from that, though. It's been towards Vulkan, where you expose in even more greater detail how the card actually works.
Is Vulkan still a state machine?
I'm sure it is.
Oh, Austin's not here.
Yeah. Boston was sitting over there. You tell us.
What happened to Austin?
I was into this graphic stuff as a hobby, like when I was Austin's age, and my knowledge of a lot of this stuff is like kind of out of date. I had to learn a lot of new things for this course, which has been super fun. I really like teaching this course, but it takes me 3 times as long as my other classes. Okay.
Isn't that just like game engine design was too?
Yes, it is exactly like game engine design was.
That's why you like teaching 492, isn't it?
Yeah. Well, you only stay in college until you get your doctorate if you really enjoy learning stuff, If you don't like learning stuff, you go make way more money than I make working for Microsoft after you just get your bachelor's degree. Okay. The buffers. Okay, so we got these buffers here. So we generate a buffer, and then we bind the buffer, which makes it the current one that we are talking about. Conversation is a state machine, too, by the way. Then we GL buffer data and go ahead and copy our data to that one. So this is where the buffer goes across the PCI Express bus. I've been talking about the whole, it's up to the video card where exactly location means, and that's actually quite true. But we're looking through tutorials. I've noticed that about half of them skip that convention entirely and just flat out say this copies it into video memory. I don't like to put in caveats like that, or statements like that aren't perfectly true. But when we run it on one of these cards, which it doesn't run on right now because it hangs, it does almost certainly copy it to video memory. No, I haven't, and it worked perfectly at home. And I connected to my home machine. We're on my home machine, doing this over my cable 1 connection. There we go. Copy all this stuff out to the currently bound buffer, which is that one. Then this next one. The input attribute, the in value there, is we're going to go ahead and get the location of that within the program. And what this gives you is a GL int that's an identifier that means something to OpenGL. Doesn't mean anything to us, just means something to OpenGL. So it's kind of like a memory address in a way. When an operating system gives you a memory address, it's not a physical address. It's just, it's an address. And it means something to the operating system. And that's about all it means. I mean, you can see if it stacks, if it's on the stack or the heap or whatever, or range. But, it gives us back an OpenGL number. Okay. So then we go ahead and enable vertex attribute array. So we're going to be talking about this one here. That's going to be the one that's enabled. We go ahead and set a pointer here to it. And so that will point it to the currently bound array. And so now at this point, we've got in value hooked up with this list right here. So that particular 7-line incantation basically says, go allocate video memory, copy this whole thing over to the video card, and then use this thing as the vertex attributes for the program when we run it. Okay. I was thinking it was going to sound simpler than that, and everybody's going to be like, man, 7 lines for that. When I actually said it, it sounded complicated enough for 7 lines, so I guess we're good. Okay, so then a transform feedback buffer. Same kind of thing in a way. We go ahead and call GLGen buffer, so we got a new buffer. Then we bind it, so it's the current one we're going to talk about. And it doesn't mean it's the vertex input attribute array. We already said what that was up here when the other one was bound. So we've changed which one's bound, and we're going to talk about this one now. And so then we go ahead and zero it all out. I don't think that's needed. In fact, I commented that line out, and it didn't hurt a thing. That's what we do. So then we'll, I commented out later, actually. I'm not sure about that. If you wrote that on your notes, just like cross it out. You can say that, yeah, okay. So it might actually be needed in order to allocate that much space on video memory ahead of time. And when I commented it out later, I was commenting out a second call to it that I was putting in for a purpose that I'll talk about in a minute. Okay, it's not like a giant secret, I'm just not there yet. Okay, so then we go ahead and enable the rasterizer discard. So this disables the rasterizer. So I've talked about the rasterizer a couple times, but just in case the term's not super familiar, rasterization is taking the primitives and turning them into fragments. So we got a triangle this spot in 3D space. We're looking at it this way. So where is it in screen coordinates? And then we take that and make a bunch of fragments, which go to the fragment shader. So when we disable this process, we're not going to have any fragments. And so that's why we're okay without a fragment shader here.
So the fragment shaders are screen relative, not world relative?
Right, exactly. Now that said, if you want to pass the coordinates, the world coordinates that the fragment came from into the fragment shader, you can totally do that, if your shading depends on that.
Like if you were doing light shading at an angle.
Yeah, because if you got some calculation where you're like, I really need to know where this fragment is from, yeah. And it'll even blend things. So it'll give you like, if you have 3 vertices that it came from, it'll average them for you into the location in 3D space that your fragment is from. Yeah. We go ahead and turn off rasterizer, and then we bind buffer base, the transform feedback buffer. So this GL transform feedback buffer is a binding location where you're expected to bind a buffer that you're about to use for transform feedback. So once it's bound there, that's where the feedback goes. So we're going to send it into TBO. Oh, I glossed over one thing too. I didn't gloss over, I forgot to say it. Okay, so see this one up here said GL static draw. This one down here said GL static read. This is a hint to OpenGL what we intend to do with these things. And so if you have one that's marked static draw, OpenGL will assume that you're going to use it in drawing operations and you're going to leave it static and you're not going to change it. If you say static read, it will assume that you're not going to change it, but you're going to read from it, from your program, and pull the results back into CPU memory at some point. And these are just hints to it. You don't have to do it that way. If we swap these two, it would still work. It would just be giving OpenGL bad information about what we're going to be doing with these buffers. So in that case, your driver might not do the ideal storage scheme. Now, I'm not sure how much it matters. The thing about the video cards, I have a bad, like way bigger card that I need to bring up here to wave around instead. The thing about the video cards is they've gotten more and more general and less weirdly specific over the years. And so it's getting to be that the management strategies for stuff on the card are a lot more, you just do the same thing all the time because you have general purpose units. It used to be that you'd have vertex shaders and fragment shaders, and they were pieces of hardware. Now they're not. You just have compute units. Okay, this one here probably does not actually have general compute units. It's that old. Okay, there we go. So we got that one set up for transform feedback. Then we say begin transform feedback, and then what type of primitive we expect. In this case, points. In fact, one-dimensional points, oddly enough. So we say GL draw arrays like we were going to draw it, but nothing appears on the screen since the rasterizer has been disabled. And then we enter transform feedback, and we run GL flush. GL flush ensures that all our commands have been run. Notice that we're not actually setting up like a loop or idle function or any of that kind of stuff, because we just want to do a couple of one-off commands here. And so we got to make sure that everything actually gets drawn. So we say GL flush, and that takes care of all the commands to date. Okay, so
is it in the fragment chair that you put in anti-aliasing?
Yeah, that would probably be the place to go. Yeah. You're gonna have to look at the neighboring fragments. I don't recall the way you do that exactly. Gee, I shouldn't say don't recall. I don't recall, but it's because I never knew. So so it's not strictly speaking inaccurate. I don't know how you access the fragment next to you, but if you can access the fragments around you and see what colors they are, then you can form some kind of blending. Okay, so the new rasterizer discard. Now, I think there's also an anti-aliasing fixed function step that can happen after your programmable fragment shader. This is a common thing to do. Could be wrong about that, though. I've always thought that, but I don't have super good proof of it. If somebody was like, defend yourself, why do you think that? I'm not sure exactly what I'd say.
So what will happen after the fragment shader?
As after the fragment shader, it's got like the fragment shader output, and so there's not a whole lot that needs to happen at that stage. Like at that point, you could write it to a frame and be okay. But I think it's got a few fixed features that it can be added onto it. It's kind of like, oh yeah, lots of times we like to do this, so we can do this to it. The user has gone into the video driver settings and they've really enabled the vibrant color profile setting. So we're going to take it and we're going to make the colors more vibrant before they go onto the screen. I know about that one. I used to actually run that one because my monitors are just a touch washed out, and so the driver can fix it for me. Okay, so anyway, but I was doing that like 10 years ago on CRT technology, maybe 15. Okay, so then at that point we turned that off, and I'm playing in the wrong spot. We can get all these numbers back out with get buffer sub data. This gets a subset of the data in a buffer. In this case, we're actually getting all the feedback from the buffer. So we're starting at position 0, and we're going all the way to the side of the end of our feedback array. Now, here's a weird thing about this. So, size of. Sometimes when people see size of and C, they're like, finally, it's like Python. I know what len is. Size of is not len. So size of here is actually going to return 20, not 5, because we got 4 byte floats. And so the size of that statically allocated array is 20 bytes. Now, if on the other hand, that array was an int star and it had been allocated somewhere else on the heap using malloc, then it would give the size as 8, because that's how big the pointer is. So it's very not len from Python. But anyway, so it's going to give you 20. So we're going to copy 20 bytes out of this feedback buffer and off to this feedback place that we have set up. And then we can print off the 5 floats, which wish I could show you that. But on the other hand, it's really not very exciting. It just prints 5 numbers. Okay. And so at that point, everything used to just kind of end on this program. So then what I spent a while doing is thinking about how to do phase 2 of that one. Let's go ahead and pop over to here, though. So I've got the ca.cpp on here. And I sort of almost feel like it'll work if I just recompile it and run it, and I haven't any good justification for that. This is just pure superstition on my part.
It's a lifetime of experience.
Yeah, so we're getting this, X code problem here. We get an X error, failed request, bad match. I'm not sure if that means OpenGL itself is broken on this computer or not. I think we have modern tutorials and 2.05. So let's see if OpenGL works. No, it actually doesn't. So we rebuild it.
You're probably missing your video drivers again.
Okay, well that works. Let's check your theory on NVIDIA drivers. So if you're ever on a Linux type machine, this one has its video drivers by the way, and you want to see if the NVIDIA stuff is set up correctly, just type NVIDIA settings like that, NVIDIA-settings, and you get the device driver control panel, and that'll tell you stuff like what driver version you're running and that kind of thing. So in our case, our NVIDIA driver version is 384.130. If the NVIDIA drivers were somehow messed up or not installed in the system, then this would tell us that it can't find the NVIDIA driver. This is also a good way to adjust your display configuration. Most distributions have a different way to adjust the display configuration as well. This one knows what it's doing. The other ones are using xrandr, so there's kind of a little bit longer pipeline to it. If you've got some way that works and you like it, go for it. And so this is where all your settings are, and what GLX extensions does this driver support, and all that kind of stuff. This is also where you can have these, you can override application settings, and you can turn on full screen anti-aliasing. And so if we say we want 8 times anti-aliasing here, this will override what our application thinks it's doing. In fact, this might even change a little bit what our cube looks like. I don't see it.
It's got rounder edges.
It's got what?
The edges are rounder.
Do they?
Kind of.
Okay, everybody memorize what that looks like? Okay. We'll turn it off. Okay, use application settings, disable, disable. Yeah, you're right. It is sharper. Yeah.
You could hurt yourself.
Interesting. Yeah, it's not very safe actually at all. So we why is this back? Well, we can go up to 16 times now. I think I was just doing a bad job on the slider before.
Let's check it out on 16 times.
Sure. That is totally better. Yeah, you're right. It's better. Probably slower too. And probably instead of being able to generate like 900 FPS, it's probably running like 700.
So is that all?
Actually, it's not, because I think we're synced. We got VSync on here. If you ever want to see how many can it really do, you got to turn off VSync. And so I forget where that is in this thing. Somewhere in here, you can actually find the there it is. So we're VSynced right here. And I don't think it'll change anything for us if we turn it off. But with the game dev class, for a little while, we were just doing everything timed with the VSync. And so if we turned it off, the game would run really, really fast. Like it was the old days and you just bought a 386.
So, why do games have settings for these things?
Well, so the game, you notice in here it had a application settings thing, right? And we set it to override application settings. We can also say use application settings. And then we just respect what your game said to do. So I think if you wanted to, say somebody's using the anti-aliasing, and they're using a computer that you have access to, and you can see from across the room they've turned it too high and they're getting bad frame rate, and you think they're doing badly because of it, then you could actually log in remotely, export NVIDIA settings to you, override their settings from their game, and turn off their anti-aliasing, and then their frame rate should improve. I think. There might be one issue there. I haven't done this, so I'm just speculating on this. The only issue that might happen is NVIDIA settings being exported to you might not pick up on what card is being used to render the display, since it will be appearing on the display other than the one on the computer is running on. may be an issue. I don't know if it would be or not.
Well, then you just have to turn the display.
Yeah, I'm sure you can get around that. If that's the only problem, I'm sure you can fix it. Okay, so anyway, that's all that stuff there. Yes, the cube works, and so OpenGL obviously is just fine in this thing. And so if we copy cube.cpp to home directory, or to say home directory here, and then we got this, and so we get there by doing that, we will get it ready for something else, which will be the other thing we've got going on, the one we just wrote. Take it on idle, take it on display, take on reset, free resources. We'll leave the glut init stuff in there. We'll leave the glue init stuff in there. We'll go ahead and not do any of those things. And we'll go ahead and we'll leave that. There's a lot of error checking in this one, which is good. And there should be error checking, right? Okay. So all that stuff is in here. We don't need that, and indeed it will just cause problems. And then we do need that. We do need that. Okay. Okay. See, that's PHP. Okay. So now we've got the entire main from before. And so if we skip over the SFML line that was hanging us up and take the rest of it, minus the window.close, and put it in here inside this other, this other one, and maybe that will help. And we still need our vertex shader source code. So there that goes. And I don't think we need any of this old main. Of course, it'll cause problems if we do. We don't need those. I'm not sure that we need that. Okay. So that'll need various things linked to it. Null pointer is not declared in this scope. Yeah, it wasn't. I'm pretty sure we can just say 0. There's another one. No PTR, 0. Oops. Okay, we'll do that too. Okay. Out value and in value are not declared. Oh, because of the version. Okay. Init resources was not declared. Yeah, it wasn't. We don't need it. So it should go away. Okay. Hey, it works. Cool beans. Okay. I don't know why it wasn't working with SFML. Can't explain it, but it works now. So there's the square roots of each thing in that list. Okay, oh, it's called cube.cpp too. That's what I always call stuff in this class. It's great. Okay, so that did it, and we're here. Okay, so that's an example of doing computation on the GPU. And although this example is undoubtedly faster than if you just calculated all 5 of those on the CPU, even if you just use one thread, if you wanted to calculate, say, 100,000 square roots, you'd probably be a lot faster with the video card. We won't do that exercise right at this exact moment, but it would actually be kind of fun. Maybe I'll do it sometime when I'm preparing examples for class, and then I can tell you if it was faster or not. Okay, so sorry, I just got stuck thinking about how to do that one. Okay, so let's go ahead and do it twice. Let's calculate the square roots of the square roots. So, not too hard to do. What we have to do, my apologies to Alex and everybody else who can't see, but that's going to disappear for just a minute because I want more screen height. We got this, we got all this stuff here that does it, right? So let's go ahead and just take all the stuff that we need, like the VBO and whatnot, and we'll duplicate it, and including that stuff. And then we'll go and take out the stuff we don't need to do it again. Okay, so fetch and print results, we do that, and then after that, okay, now do it again. Okay, so we don't need to redeclare VBO, it was already declared. We don't need to make a new buffer for it, we already have one. We'll go ahead and bind it and say we're going to use it as a static draw, sure. This in value here, we're going to go and set this, oh hey, right here too. You see we're copying data into this draw buffer, the one we're about to draw from. We want to do feedback. So we just got these square roots up there, and it's the right feedback. So we'll put them back into the beginning there and get it all set up for, around we go again. Okay, so we probably need to set that up as this. We could probably comment those out maybe, I don't know. We don't need to redeclare TBO, in fact we can't. We don't need to make a new buffer for it, it already exists. We don't need to say how big it is by putting zeros into it. I tested that once. I'll put a thing there until it actually works. We still need to disable rasterize or discard, of course. And so then we'll set the same buffer to receive everything, and so on and so forth. And then we'll fetch the results and print them again. See if it works. Okay. We're going to go back into everybody sees mode. Okay. Couple problems. GL input attribute. Okay, so we set it right there. My guess is we tried to declare it. Oh, that is the second time. So you see up here we said GL input attrib equals, etc. Well, the fact is the attrib location has not changed, so we can probably just get rid of that one. Okay, input attrib was not. I think we must have got rid of the wrong version of that. Yeah, we did. They look the same. How are we supposed to know? Okay. Is that the first one or the second one? Gotta be the first one. Okay. Oh, we made feedback again. Yeah, we did that right there. So I'm going to declare it again. That's a redeclaration. I'm going to take a few of these extra lines out of here too. Get some screen space back. That does the whole run thing as one block there. Okay. We'll do that here too. And then, okay. Whoever did this example did not expect to see it on a projector. Okay, so there's the square roots. There's the square roots of the square roots. We can do it again if we wanted. We can make it a loop to set it up and whatnot. But the fact is, we do this in a really bad way. So the reason that this is a bad way. So up there we go ahead and get the feedback off the video card. Great. So we got it in CPU memory. But then we go copy it back to the video card where it came from. And so we did need to copy it to the CPU so we could print it out. If we were doing this as something where inside the program we're just going to keep changing this or whatnot, we might not want to bring it to the CPU at all. In this case, we'll leave it, bring it to the CPU just so it prints it out. But then we're going to send it back across the PCI Express bus into the video card again. You don't need to do that. It's already in the video card. Like that's where we got those numbers, right? They're in video memory. So we should be able to just use them. And the fact is we can. So the problem there is, you see we moved from this, we put everything into the vertex buffer array. Is that what we call it? Or is it VBO? I think it's VBO. Okay. We put everything into this vertex buffer attribute or array, and then we go and do our program or shader, and then it goes out into our transform feedback object. And so then that's where it ends up in this TBO, transform buffer object, that's what we call it. Okay, anyway, so it did that. So in order to do it again, one way we could do it is take it from this one and copy it over to here. But that sounds like it's going to take extra time, right? You're going to copy? Everybody's like, how much time does it really take? The video card's fast. Well, yeah. But you don't want to copy stuff over if you don't have to. So the easy way to do it is just switch position on these two and then run it again. And then it ends up in the other one. So actually what we'll do is we'll take it from this TBO and put it back into the shader, which will put our new values into the VBO, where they started out.
Wait, what?
So we started here with this, we put all of our initial values or data there into the vertex buffer object. And so that's where it all started out, is this in value. Then we made a feedback buffer for it, and everything went into the feedback buffer. So you just got to switch. So it's really not that hard to switch. We have to do down here. Okay. Sorry about that. This is what we don't want to do, right there. Okay. This makes a copy. Don't do this. Okay, so we'll go ahead and bind the TBO buffer. And then down here, so we'll be setting that up as the input attribute. And then for the transform feedback buffer, we'll use the VBO. And so then that's where everything's going, is the transform feedback buffer is the VBO. And the fact is we probably didn't have to bind it down there. It'll get bound right here anyway. And then everything goes there. And then to take it back out, we don't have to do anything. Because we said we're getting the data out of the thing that's currently set up or bound as the GL transform feedback buffer. And what we've bound as the GL transform feedback buffer is the VBO. Okay, so let's see what happens. There we go. It is an infinitesimal amount faster now that we can see. Or probably even observe with the time command, because the loading time in this program is going to be tremendous compared to the amount of time it runs. Okay, so that's a way to go on this. And I was saying that we didn't necessarily maybe need to bind the VBO right here. Let's see. Don't need to. So we can actually take these ones out. We don't have to do that anymore. And this is what we're trying, this is what we don't want to do. So I'm going to leave this here as part of the example so you can see what we're not supposed to do. And I'm not entirely absolutely certain that we need to do that either. Let's see. Nope, don't need that. I'm pretty sure we need this one. Yeah, we needed that one. The reason we need this one, so GL vertex attribute pointer says that the currently bound array, that is the TBO, is going to be the vertex attribute information that we use when we say draw arrays down there. And so the reason we had to do that is because now this is going to be the TBO, instead of the VBO. And instead of buying this buffer as the input requires us to actually say this. Otherwise, it will still use the one we had bound previously. Remember, state machine, it holds a state. And so it was taking the initial input that it had before, 1, 2, 3, 4, 5, and using that as the input. Then it was failing to do transform feedback, because it can't take it and put it back in the same buffer. And so it's probably throwing an OpenGL error that we couldn't see. And so the contents that we were getting out at the end was the initial contents of the VBO. Okay, so that does have to be done. Okay. So I think we're cut down to the stuff that we actually have to do here. I don't think we can take out any more lines and still have it function, except possibly some of this cleanup stuff, you know. If we took out if we didn't bother to delete our program and shaders and whatnot and just return 0 and hey, we're done, you know, it'd be fine. I mean, it's like, you know, if you're renting an apartment to somebody and they've set up a meth lab and then one day they just run away and leave the whole mess, you know, it would be kind of like that. But it would work. Okay. Yeah. Okay. Make sure this thing ends up in a working state. Yes, it does. Okay. Let's talk about these this transform feedback process and the implications for it just a little bit. Being able to do this means that you can go ahead and do whatever you like in the car. This whole back and forth thing does mean you kind of have to have 2 buffers. So suppose for a moment you wanted to, say instead of just calculating the square root of the square root, we wanted to do that like 20 times. You know, you'd have to go back and forth between a couple of buffers as you went, and just kind of switch which one was the input and which was the output each time, and eventually you get it. Now, that might sound a lot like the double buffering that we use to draw things on the screen, and in fact it is. It's a lot of this stuff, computing things on a GPU, comes back to graphics stuff, graphics metaphors and whatnot. But we're starting with graphics, you know. That's what the card does. Okay, so we can do that, pushing things back and forth between buffers like this. And so the only reason this one even takes it out of memory is because we call this function GL get buffer subdata twice in order to get what's currently in there. Now we can use GL get buffer subdata to get stuff out of buffers whenever we like. But most of the buffers that we use, well, all the buffers we've been using so far, aren't intended for any kind of feedback. And so usually the buffer's content is whatever it was when we put it there. And so there's not a whole lot of reason to get it. You think about like our tree demo with the waving bush in the wind. Well, the vertex buffer array in the card is always the same. We're just changing how the vertex shader places things, or whether the geometry shader makes a copy of it or whatnot. But you know, the initial vertex, the initial array never changes. And so pulling it into CPU memory again with this just doesn't really make any sense. Okay, so that was kind of a translation feedback specific sort of call there that you really wouldn't use much at a time. Okay, so that all comes in. Now, this demo here, the length of the array is 5 floats, and that's always what it is. Now, if we were doing this from the geometry shader, remember the geometry shader doesn't have a one-to-one relationship between vertices in to vertices out. And so because of that, it's possible that you might have that the feedback could make something bigger or smaller, depending on how it comes out. And so it makes it so you don't actually know how much data is in the feedback buffer. There's a call to query for it. I don't have it written down in here. But there's also a, besides GL draw arrays here, GL draw arrays expect you to say the beginning and the end of the offset of what you want to draw. And so it expects you to know how many things are in your array. There's a different called GL draw transform feedback that is intended to draw feedback buffers where you just don't know how big they are yet. And when you use that call, it'll actually figure out how big it is on the card and go ahead and draw your feedback buffer for you, assuming you've bound it as the vertex attribute array. Okay, so there's some advantages, some things you can do there. I'd like to, at some point here, put together like a particle simulation or something using the translation feedback. That seems to be one of the more popular uses for these things online, is with like a particle system. Think about our fruit falling off the tree last time. All the fruit just falls off the tree, right? And it's on the ground. But it means for each fruit, there has to be a calculation performed about where it is. And what we did is just totally unify the speed. All the fruit falls at exactly the same speed. That can look unrealistic if the particles aren't expected to go the same way. Suppose instead of falling off, the fruit was going to be dispersed because somebody hit the tree with a rocket launcher. In that case, the fruit is all going to have different trajectories as it goes out from the tree. And so the traditional way to do that is to use the CPU, and basically for each fruit, where does the fruit go next? You know, apply the vector that shows the direction of the fruit to each fruit, and then apply a physics operation to the vector that shows the velocity of the fruit in order to respect physics. So basically take a little bit off the velocity, and then you have some gravity, so eventually it comes back down. But any of this kind of thing where you have some loop that's like for each fruit, and there's a whole bunch of fruits, this is a great area to put on the video card, since it really specializes in the whole, like, you know, for each of this giant list of stuff, let's do the exact same thing on it. We can use this stuff for that particle simulation. I don't think we really have enough time to set up the particle simulation today, but I'm thinking that that'll be somewhere that this goes in the near future. Transform feedback's been available for quite a few OpenGL versions. You probably won't run into something where you're like, man, my laptop didn't support this. I was able to run this program just fine on a GeForce 9800 GT, which is probably 10 years old, maybe a little over 10 years old. So it's been around since OpenGL version about 3 point something early, 3.3, something like that, 3.2. I don't know exactly. I want to mention something more about versions that I've been meaning to say, but haven't said it yet since we haven't had a good time, and now we've got 10 minutes. Okay. Let's look at transform feedback here on a Chronos kind of official page. And so I mentioned, oh man, that hasn't been, oh yeah, it's still core in version 4.6. So version 3.0 is where it became core. So zoom in on this panel over here a little bit. Okay, so it's been core, it's still core in version 4.6. It's been core since version 3.0, so quite a long time. Now it's got this ARB extension, ARB transform feedback 2, ARB transform feedback 3, ARB transform feedback index, EXT transform feedback, NV transform feedback. So you've got all these different kind of like prefix followed by that name, something. Name NV transform feedback, the name strings and status. Shipping for GeForce 8 series. Well, that's why it's in my 9800 GT. It started in the 800 series in November 2006. Cool. Last modified date, etc. NVIDIA revision. Dependencies. OpenGL 1.5 is required. It interacts with ext timer query. NV Vertex program 4 and all this other stuff affects it. This extension provides a new mode to the GL graphics library called transform feedback, which records vertex attributes of the primitives processed by the graphics library. The selected attributes are written into buffer objects, we saw that, and can be written with each attribute in a separate buffer object, or with all attributes interleaved into a single buffer object. I didn't show you that part. The reason is we only have one attribute coming back here, and so they're actually the same thing. Because if we have more than one attribute, we can say, okay, just mix it all up into the salad array, and it's not the salad array, it's organized, interleaved, you know? You got one attribute and the other one. So if you got attributes A and B, you got A and B, and A and B for the next one, and A and B for the next one, you see, all the way down. Or you can have, attribute A go to one and attribute B go to another. Yeah. Okay. If the geometry program or shader is active, the primitives recorded are those emitted by the geometry program. Otherwise, the transform feedback captures primitives whose vertex are transformed by the vertex program or shader, or by fixed function vertex processing, which was still a thing back then. Now, I didn't mention tessellation shaders because OpenGL didn't have tessellation shaders yet. But if there had been tessellation control shaders, it would have been careful to identify that if there's no geometry shader, then it'll capture what comes from a tessellation shader. If there's no tessellation shader, it captures what comes from the vertex shader, like you just did. There we go. So the primitives capture those generated prior to clipping in either case. And so it's basically, before you hit the rasterizer process, whatever's there is what you get in the transform feedback. Okay, yes, you can calculate that and whatnot. Okay, so this extension out. Okay. New tokens. Let's mention new tokens and stuff. Okay, so this whole thing in here for this NV transform feedback goes on for kind of a long time explaining what exactly happens and additions, interactions with stuff, errors. Tell me where it's from. Give me history, issues with it, sure. Lots of issues. Okay, maybe end it without saying what I wanted to say. That's fine. Okay, so the reason that it's an NV transform feedback is it was initially a vendor-specific addition. So in their 8 series cards, this is back when NVIDIA and ATI were still trading blows, and NVIDIA didn't have dominance in the performance market. So trying to get ahead of each other, one thing the video card companies would do, and actually they still do this, is they come out with a novel feature that makes their card better than the other, and so then they'd have to have some way to support it in OpenGL, because that's what the graphics developers are using, that and DirectX. They probably have an equivalent over there. And then the various console-specific ones, but that depends on if they're doing a console or not. So, when NVIDIA came up with this feature, they added this extension, NV Transform Feedback, as a vendor-specific OpenGL feature. I haven't shown you how to do it yet, but you can query OpenGL to say, can you have such and such feature? And then if you had a GeForce 8 series and you had the equivalent Radeon, for one of them it would have told you, yeah, you got the feature. For the other one it said, no, you didn't. So, next over here, we have the EXT, an external feature, transform feedback. And then we have ARB, Architecture Review Board. And then once you're at the ARB point, it's somewhat legitimized in that it's no longer a vendor-specific feature. It's actually something that's in OpenGL, but it's not core yet. The core OpenGL features are, the main ones. They're all supported. when there's a feature that might or might not become core in the future, something that usually was previously a vendor extension, it'll be available as an architecture review board feature, ARB, for some time. Then eventually, it'll become a core feature. And so this has been core since version 3. So if you think about the new GeForce 2080, I haven't looked at what's coming, but I would expect to see a vendor extension for this ray tracing stuff. You know, NV ray trace or something like that. And then once multiple manufacturers start to have it, we'd have it move as far as the ARB level, where you have an architecture review board feature to add ray tracing to OpenGL. And then finally, once everybody seems to be happy with the way it works, you'd have a core feature for ray tracing. Anyway, so that's how these things move in. And they're always moving in. It's not like CPUs where it feels like they don't move in that fast. It moves much quicker in the graphics world. Okay, it still works in the CPU world. You see new instruction sets like SSE3 come into use and whatnot. It's just not like every revision brings in something new. Okay, so that's how these things come into OpenGL and how the library grows. And so that's why somebody like me that played with this as a hobby 15 years ago is always looking at this being like, oh, you can do this now. And so it also means that if you take this class and you start doing this stuff and you do it a lot and then you go do it for a couple of years and you go interview with Epic or something, you should probably look at what came out in the latest OpenGL version first. Okay, so that's that part. So I think that's it for today. We're kind of running out of time here. So I'll have lab a little later. I've got a couple ideas about what to do for lab. I'd sort of like to do a computational thing where you move vertices around. But I haven't quite decided on that versus continue with the geometry shaders. The fact is I don't have a lot of people who actually sign up and done with the geometry shader lab, and so I'm expecting the first part of lab today might be debugging last time's geometry shader labs. So I don't want to make today's lab really busy. I might also have to step out a few minutes early to grab my daughter this week only, hopefully. So I don't want it to be some everybody's at the end being like, oh, we all have questions at the same time. Yeah, that's that. Okay, I'll see you in an hour and a half after the other class finishes with this room. Oh, did you see the guy that, I don't remember his name, was trying to fix the network here. We fixed it, so he should get
His name was Bob.
Bob, okay.
It's